There, chemistry fans. Right, so I'm going to go through 17.1, which is about mass spectroscopy. So I will start sharing my screen. Okay, you can see the key points behind me on this behind me. Right, let's start sharing the screen. Okay, so you should be able to see my screen now. As per usual, we've got revision is on Teams, but you should now be doing practice papers because you will have a breadth paper in the last week of June, and then you'll have another paper when you come back in September, which are they're the AS papers. So it will be covering all the first year work. Remember, workshops are Mondays and Tuesdays 1 till 2 in T101. Okay, so little quick recap. How do we know if we have a carbon-carbon bond? What tests can we do for a haloalkane? What about an alcohol? How can we test those? Okay, so really probably what you probably want to do is to pause the video now and have a go at those questions. So pause the video now. Okay. So how do we know we have a carbon-carbon bond? We would add bromine water to it, and if there are double carbon-carbon double bonds, then the bromine water will react to make a dibromo compound, adding across the double bond. So we have a electrophilic addition, and the bromine comes on and breaks the bond. You have bromine attached to both of those carbons. Haloalkane, how would you test for a haloalkane? Okay, so a haloalkane has got the bromine or chlorine or iodine in it. If you add silver nitrate to it, okay, in the right conditions, you'll actually turn it into the alcohol, and the halide will come off, and it will react with silver to form either silver chloride, silver bromide, or silver iodide. And we know the test for those. That's well, we know that silver chloride is white, silver bromide is creamy yellow, and silver iodide is yellow. And then we can tell the difference between those sort of partially discernible colors. White from cream by doing dilute ammonia with it, and if it was the chloride it would redissolve. Bromide it wouldn't, iodide it wouldn't. And to tell the difference between bromide and iodide, we have concentrated ammonia, and the bromide would dissolve, the iodide wouldn't. How do you know if you've got an alcohol? What test can you do for an alcohol? You can test it by reacting it with potassium dichromate, okay, and if you can get a positive result with that, so it goes from orange to green, then that is potentially an alcohol, okay? And you could tell it's not a aldehyde by testing it with Tollens reagent, and an alcohol would not give a silver mirror, whereas an aldehyde would. Okay, down below we have some pictures of Nobel Prize winners. These Nobel Prize winners, Joseph John Thompson, Francis William Aston, Wolfgang Paul, John Bennett Fenn, and Koichi Tanaka, all were involved in the development of mass spectroscopy. So we'll have a look at mass spectroscopy now, if I can move the slide up. Okay, so we're going to look at mass spectroscopy. So we will consider the concept of the molecular ion peak, okay, which enables us to work out its mass. We will understand that the may have a small extra peak just past the molecular ion peak, which could be because of carbon-13. Okay, and we will look at fragment ions now in mass spec. Previously, you have looked at the just the last peak on mass spectroscopy to work out the isotopic composition of elements. And hopefully, when we can use some of these molecular ion peaks and fragments to identify structures. So those are our keywords. Okay, so obviously you should make some flashcards of those, make sure you learn those. Okay, just obviously you can stop if you need to write them down, but they are on the video online. So here we have our mass spec. Okay, this is explained on page 19 to 21 in chapter 2, because you should really go over that, and that's probably a good idea. So yeah, if you pause the video now and just go over chapter 2. Okay. Okay, hopefully you've had a little time to recap yourself on chapter 2 and the principles of mass spectroscopy. So here we have our sample. It's ionized by heating it highly. Then we fire electrons through it, okay, high energy electrons. They smash into the molecules, knocking other electrons out. And that means that the sample has some fragments or completely whole pieces which are +1 because you've lost an electron. Could potentially be +2 because we could knock out 2 electrons. But anyway, they are accelerated towards the end here because this end is negative. So you know, we have an we have a high voltage difference between this side and this side, negative this side, so the ions positive, they'll smash through here. We have slits in here, so they'll go through the slits, okay, and they'll go down the mass spec machine, okay, and then under the power of an electromagnet, they could be bent, and that relates to their mass and their charge, and how much they get bent is, or deflected is the proper word, I suppose. How much they're deflected is dependent on their mass and their charge ratio. They then come down to the end of the machine, they're detected by a computer, and we get a graph. Okay, so we have our detection. So let's look on. So in chapter 2, what you looked at was perhaps having a mixture of bromine isotopes. So you could have bromine 79 and bromine 81. And you would find you'd have 2 peaks, okay, of 79 and 81. And the ratio of those peaks would be approximately 50-50, okay, probably slightly in favour of 79. And then what you do is you work out the percentage of each one, and you can put those, multiply those together. So it might be 49% isotope 81, 51% isotope 79, and that basically works out giving you an average relative atomic mass of 79.9. So we've done that. Now, if we look at what happens with a molecule rather than atoms, the molecule is ionized, and we could just smash out 1 electron and leave the molecule intact, but -1 electron, so it's +1. But it could fragment. Okay, the molecule could fragment. In other words, we could break some bonds, and guess which word is coming in here? Heterolytically. The bonds could break heterolytically, leaving 1 fragment positive and 1 fragment negative. Now, we don't worry about the negative fragment because that's not going to go down the tube, but the positive fragment will go down the tube, and it will be deflected based on its mass and its charge. The charge would most likely be +1, but we can have different masses. So we have different size fragments going down the tube. Sometimes the fragments could get rearranged and we end up having different combinations, but the combinations must relate to the actual structure of the molecule in the first place. Okay, so we've got our things going down the tube, okay, and it's now used to identify unknown or new compounds. In the past, it would have been useful for known compounds. Unknown ones, it wouldn't work so well. But now, because we can use computers, we can actually get them to analyze all the fragments and suggest what fragments we've got, and then using a database, they can put it together. So we get the M+ fragment, okay, and we got further fragments, okay. I mean, this is just explaining what I've just said. And we can have several peaks on the spectrum, but the final peak, the M+, is going to give us the molecular ion, which will have the highest value. Okay, so here we have an example. Here we've got a molecular ion peak of M+, okay, 114. Guess what? There's one at 115 as well. That is because of carbon-13, where we've got extra neutrons in the nucleus of the carbon. So that is about having isotopes of the elements. But here is our main ion here. It's 114. So that is going to be occurring due to a specific molecular ion species. This is C8H18. Okay. Now, if you think of the general formula, are there any double bonds in it? No, because it's 8 times 2 plus 2 is 18. So that is just an alkane. Okay, it is octane, obviously, C8. Now, octane, it could be straight chain or it could be branched. Okay, Can't be a ring. If it was a ring, it would be H16. If it had a double bond, it would be H16. Okay, if it well, it hasn't got any other elements in it, but yeah, that's the only possibility it could be. So it's going to be a straight chain, or it's going to be branch chain of octane, and then we'll be able to analyze it a bit further. In fact, I mean, it says it's octane, it doesn't specify whether it's branched or not. Okay, so this, in fact, it isn't going to be branched. So the final signal is due to the highest MZ value. It's known as the molecular ion, and it is the mass of the compound. So that is one thing mass spec can give you, is the mass of a compound. So, but we have got some fragments, okay, and they've got a variety of peaks, and they have different absorbance levels, i.e. which ones are more common, okay, and each peak is going to be due to different fragments, and the tallest one is the most stable. So here is the 1%, yeah, so basically the abundance of 114 should be 99%, and the abundance of 115 should be at 1%. Okay, so yeah, you can see the ratio working out there. So the more carbons present, the larger the M+1 peak. Okay, so this peak will change because you can have more carbons being carbon-13. Okay, so the more carbon, the longer it is, the more likely you'll have more carbon-13. So the peak height will change slightly. Okay, so we've got some fragments. Okay, here are the fragments that we've got from octane. Okay, we've got a peak of 29, 43, 57, 71, and 85. Those are our big tall peaks. Okay, and we can see that actually, if we look at the gap between them, so 29 to 43 is a gap of 14. 43 to 57 is a gap of 14. 57 to 71 is a gap of 14. 71 to 85 is a gap of 14. Okay, so we've got gaps of 14. Okay, and well, what could have a mass of 14? Carbon 12, hydrogen 1 plus 1. So CH2. So basically, it is showing us how we go, going along a chain of a straight chain alkane. So that one is ethyl, yeah, so you can see that C2, 24, plus 5, 29, okay, so these are the peaks, and the loss, the gap between them being 14 is CH2. Okay, what molecule might be indicated by a loss of 18? Water. What about 28? Carbon monoxide. Now, those might be quite common ones to lose because you might have an alcohol, or you might have an aldehyde or something with a carbonyl group. The carbonyl is going to give you the carbon monoxide, and anything with an OH could be quite easy to lose, H2O. So let's have a look at some fragmentation patterns. So peaks can occur at, right, so the mass of simple hydrogen atom peaks, those are going to be very common peaks to have, especially with straight chain alkanes. Okay, those are going to be very common peaks to have. 15, which is methyl group, 29 is ethyl, etc., etc. Okay, and what's going to affect the height of the peak? The stability of the carbocation formed affects its abundance. So the more stable the cation, the higher the peak. So if we've got sub-branch or branches either side of it, then that's going to make a more stable one. So the more alkyl groups it is, the more stable. So, yeah. Okay, so we then have this idea of our tertiary, secondary, and primary again in terms of stability. So if you have, say, CH3, we wouldn't expect to have many or high abundance so much because it's not stabilized very much. But C2H5, yeah, we might have to stabilize it a bit. CH3, C3H7 even more. Okay, so we're going to stabilize the ions. Okay, so some fragmentation. So the aldehydes and ketones are going to contain the carbonyl. Okay, and often the bond next to carbonyl breaks during fragmentation. So a common fragment, therefore, could be carbon monoxide. So its mass is 28, so you'd see a fragment of 28, or you'd see a difference of 28 between fragments. So you can either have a peak of 28 or a difference of 28 between two peaks. So the more stable that the carbonyl is. So we've got RCO plus, R being the rest of the molecule, the more abundant being the taller its spectrum peak. So here we have our carbonyl, okay? Could be a ketone, could be an aldehyde, could be a carboxylic acid. If we break one of those bonds, so the red one, we get RCO plus R1, okay? So this is how we get it. So let's have a look at what's going on. So this ion has an MZ of 100, okay? Here are some likely places it could break. Okay, now if it breaks in those places, okay, we're either left with those fragments, yeah? And when they break, okay, when they break, we, well, we'll look at how we do the equation later. So we have the peaks like this, and you could split either way, okay? And if we split the other bond, we could split that, and that could end up either way. So we get those various peaks, okay, which hopefully should make sense if you, and the masses should make sense if you work them out, okay. And a further peak could appear at 72 because we might just lose the carbonyl. Remember that things can, that they can rearrange as well. So if we have our molecule, okay, we can smash a high energy, fast moving electron into it. We produce a molecular ion, which is positive, and we therefore lose 2 electrons because we've got the electron we smashed into it, and we've got the electron that's come off of it. So we could write it M, molecule, yeah, not metal, but molecule, M gas, so they will be vaporized, it'll be, all our samples are vaporized. So our molecule M plus an electron becomes M plus 2 electrons. Okay, so we've got that. And because it's now, you know, a large molecule, or it's quite a collection of atoms to join together, we put it in brackets, square brackets, and put a plus up by it to show that it's a molecular ion. So when we do this, we actually have a molecular ion, a positive ion plus a neutral species, okay, because, in other words, you know, sort of like a radical, because we've lost got 2 electrons going as well. So M plus makes, let's think about this again. Okay, if this then gets hit by an ion, we can get that, okay. And yeah, so basically we've already got a molecular ion, it's fragmenting again, okay, and therefore we might end up with smaller pieces, okay, either way. So which are going to show in the final spectrum? Only the ones that are positive, that one, and that one, okay. So now then, let's have a look at a question, okay? So what I'm going to do is I'll get you to, you can pause the video now. I'll put this somewhere sensible. So pop that there-ish. There is, as it says, a user table on page 1. So I'll pop that there, okay? So you should be able to have a go at identifying that. Okay, so this is it here. So we've got 142, which is C10H22. Okay, so we've got a peak there. That's going to be a propyl peak. Okay, 43. We've got a butyl peak at 57. Okay, and we've got a pentyl peak at 71. So 43 to 57 is 14. Okay. And then we've got a 1, 2, 3, 4, 5, 6, 7, 8 octal peak as well. Okay, and we've also got our decal peak. Okay, so you know, just check that out. Right now, okay, given that 77 is 612, 72 plus 5, that's phenol. So this bit here is the phenol ring. So they're telling you that, okay, which is a benzene ring without hydrogen. So benzene ring is going to be 78. Without one hydrogen, it's going to be 77. Okay, so that's that. Okay, have a go at working what you've got there. Just okay. So let's have a look at that. So this is the compound. So we've got this bit, this fragment here, where it's broken here and left this positive fragment. That's 77. Okay. And the question is, what is fragment 43 in this case? It's not going to be propyl, because remember 43 was propyl. Okay, what could it be? Okay, it's going to be CH3CO, so it's breaking, it's this fragment here. So if we break it here, either this bit becomes positive or this bit becomes positive. Okay, if I'm leaning funny, it's because I'm looking at the screen, which is near my laptop. Okay. Right, so then we've got the rest of our peaks. That is our phenol peak, C6H5+, as we said previously. Okay, that is CO, because if I had this plus 28 makes that. Okay. So that is with the CH3, that's our final, that's our molecular ion peak. All of this, sorry, all that should add up to 120, okay. And then we've got further peaks, we've got C4H3. Okay, so C4H3 is basically a part of the phenol ring breaking apart. Okay, and CO plus is just the carbon monoxide coming off by itself, so breaking here and breaking here. Okay, right, that is pretty much it. Okay, so I'm going to finish there. There's some questions to do. Hopefully you can do those before you actually come to the lesson. And I will just finish by stop sharing my screen. Let's stop sharing my screen, which is okay. And if I move that way for a bit, you can see the summary of what we've just done.